Hello, welcome back to another day. Sorry I kind of took a break. I was really busy over the weekend and I did record on Friday, but I was really tired. I did like a Code Forces round and I didn't do so well, so I decided not to upload. Um, Today, the topic I wanted to cover was actually something really different because I actually need to like study this again and um, part of this is like at work I also kind of use this. Um, so matrix multiplication. We're gonna try to implement matrix multiplication super duper fast. I know sort of the first two techniques, but afterwards there's like tiling and sharing memory, which um, I don't remember as well. So I'd like to brush up on this. Um, so what we're gonna do is we're going to make a new project. Uh, Maybe I'll just make a new repo, new repository. Let's make it private, fast matrix multiplication, and then C++ ignore. And let's make this repository. And let's clone. So I'm gonna do this in C++, and I'm actually gonna base this off a tutorial. Well, I've read sort of the tutorial. I'm not gonna look at it again. I think it's like fast CPU matrix multiplication. Yeah, this one by Mr. Siboim. He also has a really good write-up on one that is done through the GPU, like writing GPU kernels. But okay, so what is matrix multiplications are really used everywhere, right? So I guess as a refresher, matrix multiplication. Do I have a drawing or did I make that work? Linear. So when I was reviewing, there's another recording right, where I was reviewing linear algebra, and I had a drawing of like, where does that use? Excalibur, linear equation. Yeah, like this stuff. Where did I use this stuff? Linear equation. All right, so when you look at ax equals b, like how do you visualize matrix multiplication? So I guess I can quickly make a note here on how, let's make a new drawing, create new drawing. All right, so a matrix multiplication, you can think of it as a dot product between, as a series of dot products. So your matrix is composed of, how do I draw? And then let's do another line. So that's, and then let's slightly flip. Okay. So two matrices multiplied by each other is going to be equal to, so then let's make some rectangles. So let's say it's like a 3 by 3 by 3 by 3. The way you visualize this, let's start with square matrices. So this 3 by 3 matrix, imagine there are 3 values, multiplied, oh, actually I should have like done it. Yeah, I should do it like the way he did it. So he drew like this, right? And then you have a bunch of lines. Okay, that's an easier way to visualize. So let's make it, I guess, a 5 by 5 matrix. Okay, it's like this. And then there are 1, 2, 3. This is really bad. 4. And then 5. Okay, this is really bad. This is not square. Terrible at drawing. All right, but yeah, this is a matrix. Okay, imagine a 5 by 5 matrix, and let me not have a sharp edges. Okay, this matrix multiplied by this matrix. All right, imagine like there's numbers in here. is going to be equal to another matrix. Specifically, you would have, let's say there are n rows, and then let's call this k columns. The requirement is that the second matrix you're multiplying has k rows, and then let's say this is m columns, and then you would have a n by m output matrix. M calls. All right. That's sort of the role. And the way this works is you would have this first cell is going to be given by the dot product of this cell. So let's say our background like this. It's given by the dot product of this times that. Is equal to. So this cell is given by the dot product. It's a multiply and add. So what you'll do is you'll do a dot product. So this is a 5 by 1 times a 1 by 5, right? And that will give you. So what you do is you multiply the first element together, and then the second element together, and the third element, and the fourth element, and the fifth element. If you multiply 5 by 1 times a 1 by 5 gives you a 5 by 5. So how does that work? Oh wait, if you do this, yeah. If you were to multiply a 1 by 5, if you were just to multiply this separately as a matrix multiplication, you actually end up with the 5 by 5, because this is 5 by 1 times 1 by 5, and then the first value will be equal to the first row times the first column, which is just one value. So essentially you would just have like a dot product of 25 different combinations, right? So 5 times 5 times 1 times 5, or 5 times 5 equals 25. You just have 25 different values, and each value represents a dot product between one entry point, or one value here and one value here. But in this case, that's not exactly what we're doing. We're doing a dot product, all right? Not a matrix multiplication. A dot product is essentially multiplying two vectors element-wise and then summing them. Okay. So we're basing matrix multiplication off of this. Matrix multiplication is used everywhere in machine learning and everything. It's the basis of how like NVIDIA GPU matrix multiplication is used. They're used for fully connected RNN. So they're really everywhere. And yeah, so there's like GPU implements gems by partitioning the output into tiles and then assigning them to thread blocks. Yeah, so this is the fancier stuff. And we're eventually going to get to that. But first, I want to start with the very basic implementation of how you do this, right? So I guess take a second and think about what is the time complexity of this, if you were to write it in code, right? So you have n so each of these is a n. I guess you have n by m total cells, and for each of these cells, you need to iterate k times, right? So there's k different values. Is that right? Or n. Wait, did I get this right? K rows. Yeah, n times m times. Wait, these two should be this n. These should be the same length. Wait, what am I doing? I am really stupid. It's the row times the column. So, yeah, it should be n by m nmk. Right, because what you're doing is for each of these cells that you compute, you iterate essentially over k different cells and just do a multiply and then add. And then you need to do this for n times m different cells. So that's O of n mk. And so we can implement a naive implementation of this and sort of see what is the runtime. Okay, so let's do that real quick. So what we're going to do is we're also going to do it in C++. And then we're going to have our floating type, and let's say, I need a main, and then probably like, we could use Google Test, but that's like a lot of setup, so I don't want to do that. I need to use Chrono to measure time. Okay, we need something like this. This will measure the runtime. Okay, and in our doing work, so let's think about, so our operation will be matrix multiply, and then what it will take is a pointer to A, B, and then this is our destination. All right, we're just gonna take pointers, and then what we're going to do is have 3 loops. So here I'm actually curious, like, the difference between templating this and passing it as an argument. So let's first do passing it as an argument. So int and int, I guess this is like rows, inners, int column, right? So what's gonna happen is A is rows by inners, B is inners by columns. This should be called calls. And C is rows by calls. So we're gonna have 3 for loops here. For int I, row equals 0, row less than rows, row plus plus. So the first most naive implementation that we're going to do is essentially we're going to iterate over each of these cells. So let's just start from like the first row, then iterate over the columns for call equals 0, call less than calls, call plus plus. And for each of these, right, so now we have an I and a j, or like a row and a call, and then we're going to compute the dot product. So the destination, and then for int inner equals 0, inner less than inners, inner plus plus. This is our case. So what we'll do is the destination at the row column, and here there's, okay, we need to spend some time deciding how to organize this in memory for performance, all of that later. But for now, I guess we can assume that it is, I mean, it's a pointer. So the way you index is multiplying the row times the column size, which is inners, plus call. Okay, so our destination is going to be this equals plus equals a at so we're at a given row, and then row times inners plus inner times b at b's, so for the first row it would be the first column, so plus row, and then what row are we on? Inner times calls. I think something like this, right? So at ij, at row call, the destination at row call is equal to a at the row, all right, times the width of this matrix, which is inners, plus inner. Inner will go from 0 all the way up to the width, which is inners. And then you'll do a dot product, and then on B side, your column is fixed, so that's the row, right? So the first row corresponds to the first column here. And then when you do a dot for this one, for example, it will be the first row with the second column. In which case, this is wrong. It should be column. Is it? What is fixed? The row is not fixed. The inner is right. Plus, I think this is actually plus call. Is it? Yeah, like when you compute this, it's the dot product of the first row with the second column. So the column remains fixed, right? And then the inner, and then when you go to the second row, your A's row changes to the second row, your inner changes, and then in B, you will choose whichever you started at. Yeah, inner times calls, because that's your width of the B matrix, and then you add column. Okay. Yeah, so that's our implementation, and then this is a void matrix multiply. So one is to pass it into the arguments, and the other would be to template it. Right, so we could have something like rows, inners. Well, they're really just int, so we can just make it an int inners, int calls. The difference here is that these values will be determined at compile time. So here I'm just overloading, I guess, this function. So let's see first matrix. So let's create a float, a equals new float, and then let's say int 1024 times 1024. Is that how you do it? New float. Oh, it's a, yeah, oh, wait, what am I doing? And then this should be just like n times, yeah, for now just stick with square matrices. And then what we're going to do is matrix multiply A, B, C, A, B, dest, and then the allocation should not be part of the computation. And then what we're going to do is compute this. Actually, let's just see. Yeah, this is nanosecond. Okay, we need to cast it. Did I even include? Okay, and then gen is just a macro for G++, with std subversion. Okay, so this took around 4 seconds, it seems. Millisecond. Yeah, around 4,000 milliseconds, right? Which is quite slow. And there's a few things that are happening here. So one, actually, and let's compare like how it would look like. So I need to make this a const expr, and then make these here, and then we can call matrix multiply and I don't think I can do this though. Can I do this? Guess it's about the same performance. What is the trade-off between? It's just that it's determined at runtime versus compile time. But in this case, like whether you know it at runtime or compile time doesn't really matter. Like if you know at a compile time, the compiler can do something different. So actually, what we could do is like we could put this in Godot and see what's happening. So I don't know how to read this. That's something I've been trying to get better at is like being able to actually understand assembly. Like even though I took some courses in uni, I kind of still suck at this. So our main function will push to the stack. Oh god, what happened? 03. Five. Like, where is this logic? Huh. Okay. I don't know how to read this. Shift bits of the foot to the left, the right by. So we're pushing this. We're decrementing the stack pointer. See, that's something I actually don't remember how stack pointers and things work. Dude, and also, why am I always so tired right now? Because it's freaking 12 a.m. Okay, I'm gonna continue tomorrow. I might like combine these edits tomorrow because getting quite a bit tired.